Today we are talking about the mole concept and molar mass, which is probably the most fundamental concept that we will discuss here in class. It's very important for chemistry, and everything that you do in chemistry basically has to do with moles and number of moles. So before we get into this matter, let's do a quick review here with chemical formulas. We've been working a lot with those lately in terms of determining what the formula is based on common charges of elements, or giving a name to a particular formula, or writing the chemical formula based on the name of that particular compound. The one thing I want you to remember here is that for ionic compounds, we refer to that formula as empirical formula because ionic compounds actually don't exist as molecules. They exist mostly as a network of positive and negative particles, and covalent compounds, like in this case, they exist as molecules. So that's the main difference between those two. Okay, so for a ionic compound, we refer to that formula as an empirical formula. For covalent compounds, we refer to that formula as a molecular formula. Okay, so but one of the things that we've been doing as well with the atoms is to determine what the atomic mass was based on atomic abundance. So that number that you actually see in the periodic table comes from that calculation, and that represents the mass, the average mass for a particular atom. So the usefulness of that is that now you can use those masses to calculate what is the mass of a particular compound. And by mass is, well, the mass of that molecule, the mass of that formula unit. So we have the average atomic mass of the atoms. You just have to look at how many you have in that particular chemical formula, and then you multiply accordingly, and then you obtain the formula mass for that particular compound. In this case, we have a covalent substance. When you calculate the formula mass for a covalent substance, you are actually calculating the molecular mass, and that number will represent the mass of a molecule. And you do that, well, we can do it the long way, in which you build a table, and basically you do a count of atoms, the type of atoms that you have. In this particular case, you have carbon, hydrogen, and chlorine. That's what you put in the first column here. You count how many of each one of those you have. You have one carbon, one hydrogen, and 3 chlorine atoms. You know the atomic masses of each one of those elements because you can get it from the periodic table. You multiply by the corresponding numbers, and you add everything together, and what you obtain here is the molecular mass for that compound. Okay, and we can do exactly the same thing for an ionic compound. The only thing is that the formula mass for an ionic compound is not the molecular mass. It's just a technicality. You don't have to worry too much about it. You need to know the difference, but we don't refer whatever formula mass you calculate for an ionic compound, we don't refer that as a molecular mass. Okay, in this particular case, we have aluminum sulfate, and when you are determining the formula mass for any substance, if you see something like this polyatomic ion and is within parentheses and there is a number outside that parenthesis, well, usually you want to eliminate that parenthesis so that you have a better count of atoms in that formula. You build your table. Again, you pick all the elements that are there. You count how many of each one you have. You multiply by the atomic mass, and then you add everything together, and you obtain that number. Now that number is not the molecular mass. We just refer to that as a formula mass. And just between you and me, if you actually tell me that this is the molecular mass for any substance, that would be okay. I'm not gonna get picky with this. So calculating that mass is important because now we can talk about the mole. And now we are not working with animals here. So this little fella here, now that's the first and last time that you're gonna see it, because we want to work with the mole from a chemistry point of view. And what the mole represents is a measuring unit. And what is measuring? Well, it's measuring quantity of matter. Now the thing with the mole is that it's more similar to one pair or 1 dozen, and what that means is that these are counting numbers because one pair represents 2 units, 1 dozen represents 12 units, while the mole also represents a certain number of units. What units? You name it. It's whatever you think, whatever comes to mind actually. However, this is a chemistry class, so we'll be thinking more in terms of atoms, molecules, and ions, but technically you can use the mole concept for everything. Okay, bottles, chairs, balls, you name it. So if we refer to the mole as a counting number, well, what is the number? So the number is actually a really large number. It's 6.022 10 to the power of 23 units. Should you memorize that number? It won't hurt you if you do, but it's going to be on the periodic table that you will receive. And the one thing is that this number receives a specific name, so whenever you see Avogadro's number, that's the number that has to come to mind. And if you see that number, then this is the name that has to come to mind. Okay, those two go together hand in hand. And where does that number come from? Well, it's actually a convention, and we go back to our friend carbon-12 atom, because we define the mole as the number of atoms present in 12 grams of carbon-12. Remember, and this is specifically carbon-12. And every single atomic mass in the periodic table is using carbon-12 as a reference. Carbon-12, not the carbon atom, specifically the isotope carbon-12. Okay? So here you have the relationship. 1 mole is the number of particles. For carbon, that number of particles have a mass of 12 grams. Or in other words, 12 grams is 1 mole of carbon-12. Okay, and just to remember, 1 AMU is 1/12 of the mass of carbon atom, and this is actually where everything comes from. So to make it a little easier for everybody, those definitions are in place so that you refer to that to quantities that you can actually visualize, like the mass of 1 carbon-12 atom is 12 AMU, but now the mass of 1 mole of carbon atoms, of carbon-12 atoms, is 12 grams. So the important thing here is that you see a triangle here, because now you have sort of a 3-way conversion factor that allows you to convert between mass and number of particles, and that number here, the mole, is basically the middleman in this transaction. So the good thing about the mole is that it stays constant for any substance that you use. For example, if we switch to sodium 23, the concept of mole stays the same. 1 mole is still representing that number of particles, but because sodium 23 is a different atom, is a heavier atom, has a larger mass, the mass changed. Okay, it increased because it's a heavier atom, but still 1 mole is still represented by the same number of particles. Heavier particles, yes, but it's the same number of particles. And still, the good thing is, not only it applies for different atoms, but you can extend that to molecules. Okay, here, 1 mole of this molecule is chloroform. It's still, that mole, that definition stays constant, is the same number of particles. Before they were atoms, now we have molecules, because it depends on what you are working with. Still, same number of particles. It's a more complex structure, and you have more atoms here, so you end up with a heavier mass because you are adding all those masses together of the individual atoms. Okay, and this number that you have here when you are doing this for this molecule, well, that is actually the molar mass. It's the mass of 1 mole of the substance. And the good thing of these conventions, when based on carbon-12, is that when you calculate the mass in grams, is numerically is the same mass in AMUs. Okay, everything has been established in such a way that that relationship stays true. Numerically, molar mass in grams is equal to the molar mass in AMUs. So we can extend those relationships, the mole relationships, to what you have in the compound in terms of the elements. So here we can say that 1 mole of chloroform contains 1 mole of carbon atoms, 1 mole of hydrogen atoms, and 3 moles of chlorine atoms. Okay, we can extend that relationship to mass relationships because we know that 1 mole of chloroform is 119.37. You have 1 mole of carbon, so 119.37 grams of chloroform will contain 12.01 grams of carbon, 1.008 grams of hydrogen, and 3 times 35.45 grams of chlorine. So you can establish that from the point of view of moles, or you can establish that from the point of view of mass, always accounting for the number of atoms that you have there. How can we put this to a practical application? How about we calculate how many moles you have in 45 grams of iron sulfate? A little check on nomenclature here. Iron 2, that's Fe2+, and sulfate is 2-. If you switch those charges and simplify, then you have FeSO4. If you are to calculate the molar mass for iron 2 sulfate, then we can do it like in the table. We have 1 iron, 1 sulfur, and for oxygen, so for iron it is 55.845, for sulfur is 32.06, these are grams. For oxygen, you have 4 oxygens and you have to multiply that by 15.999, which is the atomic mass for oxygen. You add all this together and you obtain 151.901. Because it's the molar mass, is the mass that 1 mole of that substance is. So you write this as grams per mole, and what you see here is a ratio of units that for you at this point a ratio of units represents a conversion factor, and that's exactly how we're going to use molar mass. Molar mass is basically a conversion factor that will allow you to calculate between number of moles and mass of a substance. Okay? So we have the mass of iron sulfate. So 45 grams of iron sulfate times, you need to cancel grams, so you have to flip that molar mass and say that 1 mole has a mass of 151.911. That takes care of the grams, and then you end up with 0.296 moles of iron sulfate. We can make it a little more difficult. How about instead of giving you the mass, I give you the volume. You still need the mass, but if I give you density, then you can calculate that, correct? So you have volume, you have density, you can calculate mass out of this. This is chloroform, we already know that, and in the previous example I used sort of a table looking data to calculate the molar mass, but this is how I want you to calculate it. So let's say you have chloroform, right? And the first element is carbon. How many carbons you have? Just 1, right? So the mass of 1 carbon atom is 12.011. Next is hydrogen. You only have 1 hydrogen, and the atomic mass of hydrogen is 1.008. And then you have 3 chlorines, and the atomic mass of chlorines is 35.45. That is how I want you to do it. It's a lot faster, and it shouldn't give you too much trouble to do it. So when you add all this together, you obtain 119.37, which is what we had before. Okay, so density is a conversion factor, molar mass is a conversion factor. You can connect all those to calculate the number of moles in that volume. Thing to remember is that 1 milliliter is 1 cubic centimeter, so I can just replace that unit in the density to make calculations a little faster. So we start with those 2 milliliters times 1.489 grams which is the mass of 1 milliliter. And then at this point you have grams, that's the mass. With the molar mass, you obtain the number of moles. And that is 0.0249 moles of chloroform. But we are not done yet, because it's also asking how many chlorine atoms are present. Now, it's the number of chlorine atoms, is not the number of moles of chlorine in that amount of matter. So we can start here, because after all, it's a molar relationship between the number of moles of a molecule and the number of moles of chlorine that you have there. So we start with 0.0249 moles of chloroform, and you have 3 moles of chlorine in 1 mole of chloroform. Because you want the number of atoms, then you need to multiply by Avogadro's number, because Avogadro's number tells you that there is 6.022 10 to the power of 23 atoms in 1 mole of chlorine. This cancel with this mole cancel with this mole, and after this calculation you should obtain something like 4.51. Actually, it should be 4.5. 10 to the power of 22 atoms of chlorine. And that would be the answer to the second question. Now, how about this problem? In this case, we have that 1 can of soda contains 40 grams of fructose. And here we have the formula, the chemical formula of fructose. And the question is, how many molecules? How many molecules should point you in the direction that you need Avogadro's number? You have mass, that means you also will need the molar mass. Okay, so if the formula is C6H12O6, remember, this is how I want you to do it. 6 times the first atom, well, of course 6 carbon atoms times 12.011, and we add, you have 12 hydrogens times 1.008. Last but not least, you have 6 oxygens times 15.999. And then the molar mass of fructose is 180.156 grams per mole. So you have the molar mass, you already know what the Avogadro's number is, you have the mass of fructose. So the sequence is, you have mass, then you go to moles, then you go to number of molecules. And to do that, here you need molar mass, and here you need Avogadro's. Okay, so we start with the mass, 40 grams, times the molar mass is 180 grams. That 180 is at the bottom because you need to cancel the grams, and that is 1 mole. Because you are calculating number of molecules, then you need 6.022 10 to the power of 23 molecules per mole. And that would be equal to 1.3 10 to the 23 molecules. So this is how you calculate molar mass. You add the atomic masses times the number of atoms for that particular atomic mass. You add them together, that's the molar mass, and you can use the molar mass to calculate the number of moles of any substance if you have the mass of that substance. Okay? If you need to take the extra step of going to number of molecules or number of atoms, then you have to multiply by Avogadro's number. Okay? And